Welcome to this special Inspenet interview. We have Frank Sapienza with us. He is a corrosion materials specialist at Betch, and in honor of their 60th anniversary, we're going to do a special interview with him. But before that, we want to show you the presentation he just did on corrosion analysis of light coker gas oil piping. So watch that first, and then we're going to have a quick Q&A session.
All right, I think we're all good, so we'll go ahead and get this presentation kicked off. My name's Frank Sapienza with Betch. I'm a corrosion materials engineer and group lead in our CMI division. I heard earlier Sam and Bobby debating their 43 versus 47 years experience. I'm at 11, so tried to catch up with them, but I still got a ways to go. But spent most of my career as a corrosion materials engineer. Started with Exxon in Chalmette. Been with Betch about 4 years now. So stick to the technical route, and I've definitely been enjoying my time. What we're going to talk today about is corrosion analysis we've done on light coker gas oil piping. Sam introduced some of the different damage mechanisms of coker, so it was a nice introduction. We spent a lot of the conference talking a lot about the drums, and there's a lot of issues with the drums, but there are, other units or other sections of the coker to also consider. Little background here. This is carbon steel. Some people call it LCGO, KGO, light coker gas oil piping. Sam had a nice diagram earlier. I'll pull one up in a second. But we had a corrosion issue, and we ultimately needed to understand what happened, why it happened, and how we can prevent it. This piping was operating about 360 to 430, so relatively low temperature in terms of corrosion, high temperature corrosion mechanisms. Typically averaging about 400 degrees. Low pressure, but really what I'd highlight here is the sulfur and total acid number. So fairly high sulfur, 2.5 weight percent. And the total acid number had a wide range. Total acid number is used often to understand the naphthic acid content. I'll talk a little bit more detail about what that means in this context as we progress through the presentation. But you can see a wide range in total acid number from 0.2 to 1.5. 1.5 is certainly on the high side of the total acid number in this service. Just to calibrate where we are in the unit, this is the light coker gas oil draw, and where we had this corrosion issue is the bottom of the stripper section right here. So piping coming off the bottom before we got to the pumps. And this is what kicked off the whole investigation, right? Unfortunately, we had a loss of containment. You can see a fairly small thin bulb right there. And you can't see it too well in this picture, but this is actually the valve right here. If you get real close, you might be able to. So right near the weld, we had a very small pinhole leak. Ideally, right, we understand the damage mechanisms, specify an inspection program, and we find the damage before it finds us. In this case, unfortunately, the inverse was true. Because of that, we wanted to make sure we understood why did this happen and how can we prevent it. When we do that, we think about one of the potential damage mechanisms that may have caused this failure. I'll talk through 4 different hypothetical proposed damage mechanisms, and then through laboratory testing, we did a series of analysis to test that hypothesis and refine out what we think the damage mechanism was. One of the first ones that we potentially considered was CO2 corrosion. CO2 corrosion is something which can occur in an aqueous phase. CO2 causes carbonic acid to form, giving a low pH, water-type material. The CO2 in a coker would come from degradation of naphthic acids, typically, which produce that CO2 as a final degradation end product. Now, if you recall, the temperature being around 400 seems too high for aqueous corrosion, but when you get these small local pinholes, you think potentially of an acidic mechanism. So we wanted to consider that as a potential damage mechanism. Sam showed this in his presentation, sulfidation, also known as sulfidic corrosion. This comes from a reaction of sulfur components in the hydrocarbon with the steel. Typically occurs above 500 F. So again, this mechanism, probably not the primary driver because of the lower temperature. Generally you see more accelerated corrosion as you get above that 500 F threshold. And being carbon steel, it could be a susceptible mechanism because carbon steel has the highest vulnerability of the low alloys to sulfidation. And again, 2.5% sulfur, so we know we have the sulfur present to cause sulfidation. Naphthenic acid corrosion. As was discussed, this is typically only present in the feed section of the coker. You may see it flagged in 571 on some of these side draws, but naphthenic acid typically degrades in the furnace and in the high temperature section and is not typically still present in these light coker gas oil cuts. But recall, we did see a tan measured of 0.2 to 1.5. So that does beg the question, is naphthenic acid potentially still present and causing corrosion here? Now, I won't get into all the details of what naphthenic acid corrosion is. People spend their whole career studying this mechanism. But essentially, this is a interaction of a specific corrodant, the naphthenic acid, in combination with sulfidation, preferentially corroding the steel. And the final damage mechanism I'll discuss before we get into the lab analysis is organic acid corrosion. We differentiated this from naphthenic acid corrosion. It's very similar, typically triggered by the carboxylic acid present, but it differs in that this is focused on the smaller, lighter carboxylic acids, which are a degradation product from longer chains. These are not actually a degradation product from the naphthenic acids. So a somewhat different mechanism, although can present itself in a similar manner by attacking that iron sulfide scale and causing accelerated corrosion. All right, so we discussed some of the potential damage mechanisms. Now let's get into the analysis and try and understand what mechanism do we think was responsible for that corrosion. This is a cross-section with the pipe. This is actually the bottom side here. What we look for when we do these cross sections is obviously the localized type pitting corrosion, which we see here. But we also will look for the degree of thinning around the circumference. It was noted that there was still relatively full thickness in other sections outside the localized corrosion. If we had just a pure sulfidation type mechanism, you'd see more uniform thinning around the entire circumference. You might see some preferential thinning, but also accelerated more throughout. Here we really saw near full thickness in the area outside of the primary corrosion zone. Now this is another macroscopic image, which is very helpful in understanding the morphology of the corrosion. Obviously, when you're looking from just the OD, you only see that very small pinhole. So if you had just replaced that pipe, thrown that elbow in the trash, gone back in kind, and kept moving forward, you really wouldn't have had a good idea of what's going on. This is pretty telling in terms of our corrosion. The failure was located near the well here where it was most severe, but as you can see, a lot of pitting throughout the bottom section of the piping. Some signs of kind of turbulent flow effects, perhaps at the well and downstream, and this pitting type morphology. Now the next steps from there is to take a cross section. We do a mount and a polish in the metallurgical lab. This is actually the fail area where the hole occurred. And you can see these other pits which were present in the macroscopic image. We note some flow type effects, so maybe some differential and thinning on one side of the well versus the other, as well as these flow type effects related to the pitting here. You can see that nice shape. indicates flow type turbulence effects. So these are all pieces of evidence that we built to understand the corrosion and identify the mechanism. Another very powerful analytical technique is looking at the corrosion scale. So different mechanisms produce different types of scale when they interact with the metal. We use a technique here called SEM and EDS. So SEM is scanning electron microscopy. And what we're doing here is using an electron microscope, actually firing electrons into the mounted sample. And those electrons will excite the scales in the metal, and that actually causes some characteristic X-rays to come back out. And those X-rays can be used to understand the elements being seen in the scale. This is a nice color-coded image of what we're seeing in terms of iron sulfide as oxygen. Now, if you're colorblind like me, sometimes you get a little bit confused with some of these images. So I'll have some other more easy to interpret images in the next slide. But what we found was a mix of sulfur-rich scale, which was nearest the iron surface. So this is the base metal iron. Then you have this corrosion layer. And then we saw this more porous ondite scale. So what you're actually seeing is the corroded sample mounted in an epoxy mount. So all these black dacks are just kind of pores and porosity that is filled with epoxy in the mount. So nearest the metal surface was heavier at sulfide, nearest the process surface heavier at oxide. Now what we can do is we can take this image and we can differentiate between the actual scale species. So here we look at just the oxygen and just the sulfur. So now we can see this sulfur is not really present in this oxide scale. It's just a tight layer of sulfide scale, very, very small. We're talking a few microns thick. The iron would be over here, and then we have this thick porous oxide scale outside the sulfur layer. So we have kind of two definitive scale zones, one of oxide, one of sulfur. And these are typically iron oxides and iron sulfides, obviously. One last type technique is just to do a line scan to understand how are these changing with time. So that color-coded image shows kind of where the zones are, but this can show us orientationally where we get a change. So we look at three elements again: sulfur, oxygen, and iron. And we go from the side starting here is the process surface into the steel. So you can see as we progress, we have a mix of this oxygen and iron, indicated iron oxide type layer. Then we hit that very thin, small sulfide-rich scale and see a large spike. And as we hit that, that's also where we see a drop-off in oxygen. So we're shifting from an oxide-based scale to a sulfide-based scale. And then honestly, we get the base metal iron and all of our scale corroded goes away. So this is all, again, building evidence into what we see. We see this oxide-rich scale on top of a sulfide-based scale, which is nearest the metal surface. We didn't see any signs of aqueous-based corrosion, right? These kind of tight scales and oxide scales, these are typical of high-temperature mechanisms. So we're thinking the sulfidation, nap acid, organic acid corrosion. We didn't see saltine or signs of acidic-type corrosion. The morphology is not fully sulfidic. If it was just sulfidation, we wouldn't see that buildup of that oxide scale on top of the sulfide layer. So we can rule out just a straight sulfidation mechanism. So which leaves our naphthenic/organic acid type corrosion. This mechanism and oxide sulfide scale is fairly characteristic of what we see in nap acid. One minor difference is usually in nap acid we start to see a more mixed sulfide and oxide layer versus such defined interfaces. But again, it goes back to the original discussion of naphthenic acids really are not present here because of the thermal degradation. So why are we seeing a naphthenic acid type attack? Now recall it was noted that the tan ranges from 0.2 to 1.5. What are we seeing here? In these coker surfaces, the naphthenic acids will break down but we still have these lighter carboxylic organic acids present. And these will often partition to various draws. So what we propose is that the corrosion is not aqueous-based, but it is certainly a direct hot type corrosion. And this is occurring due to these lighter non-naphthenic acid carboxylic acids, which have a less than C10 carbon weight typically. What these do is something very similar to nap acid, where they actually dissolve at iron sulfide scale and they allow a continuous attack of the steel. And that often presents itself as a pitting type mechanism, which we saw. These typically occur near the boiling point of those acids. So naphthenic acids are most corrosive near their boiling points, but those can be at much higher and elevated temperatures. This was operating 350 to 420 F, so fairly low. But as you get to lighter acids, the boiling point of those acids will also be lower. So although we don't have the full chemistry yet of the stream, we suspect that some of these lighter carboxylic acids have boiling points in that 350 to 400 range where they're most corrosive. And that's why we saw this accelerated pitting type corrosion occurring. So what are some recommendations and what can we do about it? We want to continue to monitor the tan to see if things change in some operation, shows higher tan versus lower. But there's other analytical techniques we can use. One is called SCAN, which is a specific carboxylic acid number. So this will help us differentiate the carboxylic acids from other acidic species which may impact the tan. One of the issues with tan is when the nab acids break down, they'll produce acetic acid, which can be flagged as a high tan number. But it all convolutes when you're just doing this single neutralization through tan. So doing some additional analytical techniques will help us understand really what species are truly present in that stream. These are techniques which are not typical in a gas oil stream. You have to kind of go to an additional level of analysis. So typically these would not be done unless you suspect an issue such as this. When we look at alloy upgrading, unfortunately an upgrade to the low chromes or 5 to 9 chrome would not be sufficient because of this pitting localized type corrosion which we're seeing. In this case, similar to a nab acid, 316, it would be an appropriate upgrade choice. We also discussed the use of an inhibitor similar to a nab acid type inhibitor. Those are the sulfur phosphorus based inhibitors. Discussed those with Sam Lordo, among others. We think it would likely be effective. The main issue here is the lower temperature. These inhibitors require a certain activation temperature, and at this lower temperature that may not be hit, but that would have to be validated before use. Sorry, one more. And then just in terms of inspection, we saw that pitting type corrosion, right? This is a localized mechanism. Now, if you only flag sulfidation as your damage mechanism in this zone, you're probably going to just do some 4-point UT in maybe 10% of your components, and you certainly would have missed this technique. So you do need to consider, are these coker gas oil streams susceptible to localized corrosion? And if they are, do things such as UT scrubbing or radiography, where this would readily be detected. Once you've got to do those localized techniques, you can dial back the inspection if you feel confident in your IOW systems and that you're only suffering from the more typical uniform corrosion. As Sam mentioned, usually the corrosion in this zone is pretty moderate to mild, so this is a somewhat unexpected mechanism. So there is still some further investigation in terms of the upstream feeds that need to be done to understand why was this specifically occurring, because we don't see this in many coker gas oil streams. One thing that may contribute to it is if there was any renewable feeds run from renewable feeds run to the unit or through the crude unit, which ended up in the coker feed, as that specifically can affect some of these lighter carboxylic acids. So certainly an interesting case, and hopefully you could take something away from it to investigate if a mechanism like this is occurring at your plant.
Thanks, Frank. Questions? Go ahead, first.
Can you talk a little bit about the scan analysis for carboxylic acid? So doing a tan measurement is kind of a blunt force measurement. It's going to capture all the acids.
Exactly.
So if scan is not easily accessible, but I was curious to know, can you talk a little bit about that analysis?
Yeah, I mean, really what it does is it differentiates just those carboxylic acids. So in my history, I have run the scan where we were getting high tans in a gas oil stream and we're concerned about nap acid corrosion. And we were getting tans of 1 to 1.2 and the scan was 0.1 or less, right? So it'll differentiate those carboxylic acids. I think generally in these coker gas oil streams, it's the acetic acids and the nap acid degradation products which are giving you those tans because that's just a neutralization number, right, through KOH titration. So if you're getting some of these other organic acids, which Sam mentioned can go into the overhead and cause some low pH in the overhead, some of those may partition to especially the LCGO or LKGO stream. So in this case, the site hasn't done that analysis yet. I'm not entirely sure what it'll say, honestly. I suspect we'll still flag something because we think that the carboxylic acids are the corroding species. Now what would be even more important would be, can we differentiate the lengths and the sizes of those carboxylic acids? That would be some additional analysis that may be even more involved.
Just a curiosity, if you check what was the salt point in the overhead, and you absolutely discard any salt position in this low point. Saying that because we have a reference of a couple of FCC units in the LCOC, where we remove salt sometimes, and they found a localized corrosion into salt position, ammonia chloride.
Yeah, no, I agree. We've seen that in other kind of coker draws as well, maybe in the upper section on like the reflux and whatnot. But in this case, we didn't see any evidence of salting, no chlorides, no solid deposits, anything like that. So,
when you made your section, were you able to do that without washing it?
Yeah, they did investigate right after the leak and didn't see any deposits or anything like that. So,
Anybody else?
Yeah.
So in the last one, so in your EDS analysis, did you look at any other metals, elements?
Yeah, so we did do the full EDS. I just included those which were actually flagging, but that was where we didn't see any chlorides or other corroded species. I don't recall if like sodium or any of the smaller lighter metals were present in terms of things like that. But
if there's something amazing, I'm sure you.
Yeah, but nothing. None of the other typical corroded species were present. So,
Brian?
Did you attempt X-ray diffraction?
A little loud, but
Did you attempt X-ray diffraction?
No, we didn't. X-ray diffraction, honestly, not a lot of labs do it. This lab can do it, but to do so, you need to get enough scale off of it. And when we did the EDS analysis, it was kind of pretty clear that there was an oxide scale and a very, very thin sulfide scale. Now, the X-ray diffraction could have told us the exact nature of that oxide and sulfide scale, but for the purpose of the investigation, we didn't feel like there was any added value at that point in terms of getting maybe the exact magnetite or exact type of oxide scale. But certainly could be done. It just there's always the time cost benefit of it. But it's a good question. But I struggle getting XRD done actually quite a bit.
Anybody else? One last one. Go ahead. 2.
So, were there any other corrosion in the LCGO pump around?
Yeah, so it seemed like this was focused mostly from the stripper to the pump. This was only a 6-inch line, so they were able to RT most of it. And there were 3 other sections with very similar pitting type morphology, just hadn't leaked yet. They are still doing the inspections downstream of the pipe, so I'm not of the pump, excuse me. So I'm not sure how far down the rundown line that this corrosion actually extends. But they didn't see any corrosion, I think, upstream of the stripper. It was only from the stripper.
The question is, why do you think it
Yeah, that is a curious one. I think because this was actually elbows, I think that was the highest velocity area on the extradose of the elbow. So this was a bottom elbow essentially turning down. So I think it was more a flow effect than a partitioning of corrosive things.
Where you detected it were.
Yeah, they were all on the extradose of the elbow. Yeah.
Did you have one, Sam?
I just have one quick question. Is this a steam stripper?
That's a good question. I have to follow up on that. I don't recall. It is.
Because you can have water down there.
Yeah,
You'd be
right.
surprised how long water will survive.
Yeah, and that was interesting about the aqueous mechanisms. Typically we'd
It's
see.
still organic acid.
Right. Yeah. Typically we'd see. A more clean pit if there was more aqueous organic corrosion.
Frank, that was a really interesting talk. So now we're just going to ask you a few questions, essentially about your presentation. So the first question that I have for you is, what are the typical damage mechanisms in coker fractionator piping?
Sure, yeah, good question. So what we typically see in the coker fractionator piping is sulfidation. That's the primary mechanism, generally a uniform type mechanism. In this case, what we saw actually was a more localized organic acid type corrosion. That's atypical of what's seen in the fractionator, but sulfidation, a readily inspectable type mechanism, is the typical mechanism.
Okay, interesting. Frank, question number 2, are welds more susceptible to corrosion than the piping?
That is always one of the common questions with mechanisms, is it going to attack the welds more, or the heat affected zones of the welds more? In these cases, we do have some amount of flow effects to the corrosion. And so when we have flow effects, the welds are always a zone that's more susceptible. There's some turbulence that occurs near the weld because of the weld root and the interface with the piping. Now, when that turbulence occurs, it will cause some accelerated corrosion in that zone. So a good inspection program should certainly consider the effect of accelerated corrosion near the welds due to the turbulence type effect in the service.
Okay, great. And Frank, last question, when is it useful to perform the more detailed laboratory analysis after a failure?
The laboratory analysis can be very useful. When we have a failure, we typically ask one of two questions. Was this a known mechanism and we just didn't inspect for it properly? Or is this something new which we perhaps didn't predict? When you have a known mechanism and you have a good inspection program, you typically don't need to go to a full failure analysis if you feel like maybe there was just a small gap in the program or something occurred which you predicted just didn't catch in time. When you have a more unknown mechanism or unknown damage mode, that's often when the laboratory analysis can be helpful. When you're trying to understand what's the profile of the corrosion, how do I assess this mechanism, and where may I see it in the future, a laboratory analysis can help you tie down the actual damage mechanism. So it does that through analysis of the corrosion product, corrosion scale, the morphology of the corrosion, and all that ties into typically a reference back to, say, API 571 to assign the damage mechanism we think caused this failure. So in summary, I would really say when a failure mechanism occurs and you don't really understand why did it occur, that's when I'd move to a laboratory analysis to do that additional techniques to understand the nature of the corrosion.
Okay, awesome. There you guys have it. Frank Sapienza from Betch. Congratulations on your talk that you just gave and also on your company's 60th anniversary. It's been a pleasure for us at Inspenet to be here at the Coker workshop covering it. So yeah, any last details?
No, I appreciate the opportunity to present with you guys.
Awesome, Frank. Thank you so much. Have a great day.
Thank you.
At Betch, our mission is simple: deliver technical excellence to our clients worldwide. From the oil and gas sector to refining and industrial processes, we provide engineering solutions that make a difference. Our expertise extends to plant services, training, and software tools, always striving to exceed our clients' expectations. At Betch, we combine cutting-edge technology with a team of experts dedicated to safety, efficiency, and innovation. Our commitment to training ensures that our teams and clients are always a step ahead. Betch, more than a company, we are your strategic partner in engineering and plant operations. Betch, good, better, Betch.